Let's look at the hypergeometric distribution. We have an urn with 4 red balls and 8 blue balls. So the urn has 12 balls. That's the only time we use the word urn in society. It's when we're talking about probability problems or ashes. We pick 5 balls from the urn without replacement. Find the probability that 3 balls are red. Well, overall, the number of ways to pick 5 balls from 12 balls is 12 choose 5, or 792. Each of these 792 ways is equally likely. How many of these 792 ways have 3 red balls and 2 blue balls? Let's count them. The number of ways to pick 3 red balls from 4 red balls is 4 choose 3, or 4. The number of ways to pick 2 blue balls from 8 blue balls is 8 choose 2, or 28. Thus, the number of ways to pick 3 red balls from 4 red balls and 2 blue balls from 8 blue balls is 4 choose 3 times 8 choose 2, which is 4 times 28, or 112. So, again, the numerator is the number of ways, the denominator is the number of ways you can pick 5 balls from 12. The numerator, more specifically, is the number of ways you pick the number of ways you can pick the 3 red balls and the 2 blue balls. And so our answer is going to be 4 times 28 over 792, in other words, 112 over 792, which is 0.14. More generally, suppose we have an urn with N1 red balls and N2 blue balls, so that the urn has N1 plus N2 balls. We pick R balls from the urn. Find the probability that X of the R balls are red if we pick the balls with replacement. Well, if you're picking balls with replacement, that's a binomial problem, and X, the number of balls that are red, has a binomial distribution, and that's the PDF for the binomial distribution. If you pick the balls without replacement, then X is said to have a hypergeometric distribution. And in this case, f of x would be n1 choose x times n2 choose r minus x all over n1 plus n2 choose r. And why is this? Why is this the probability that if you pick r balls, that of those r balls, you'll have x of them, why is it that x of them will be red and the others will be blue? How is that? The denominator is the number of ways to pick r balls from n1 plus n2 balls. It's n1 plus n2 choose r. The numerator is the number of ways to pick x red balls from n1 red balls and r minus x blue balls from n2 blue balls. So again, we're picking r balls from the n1 plus n2 balls. The numerator is just counting the number of ways you can have x of those balls be red and the rest of them, r minus x of them, be blue. Again, suppose we have an urn with 4 red balls and 8 blue balls, so the urn has 12 balls. We pick 5 balls from the urn without replacement. Let x be the number of red balls. Find the mean value of x. Well, it seems reasonable that the mean of x, mu sub x, would be 5 times 4 over 12, because again, 4 of the balls are red. So it seems reasonable that on average, if you pick a ball once, if you pick just one ball, the probability that it's going to be red is 4 over 12, in other words, 1/3. So if you pick balls 5 times, the expected number of red balls would be 5 times 4 over 12, in other words, 5/3. More generally, suppose we have an urn with N1 red balls and N2 blue balls, so that the urn has N1 plus N2 balls. We pick R balls from the urn without replacement. Let X be the number of red balls. The mean value of X, the number of red balls, is going to be R times N1 over N1 plus N2. Again, what's in parentheses is the probability that one particular ball is going to be red, N1 over N1 plus N2. And R, that's just the number of balls you pick. So again, that product, R times N1 over N1 plus N2, that would be the expected number of blue balls if you pick R balls overall. Okay, well, enough with balls. Let's talk about cards. We pick 5 cards without replacement from a deck of 52 cards. Find the probability that we pick exactly 3 hearts. The number of ways to pick 3 hearts and 2 other cards, so this would be the number of ways to pick 3 hearts and 2 other cards over the total number of ways to pick 5 cards. We've seen that denominator before. That's 52 choose 5. That's the number of 5-card hands, essentially. The numerator is the number of 5-card hands that have 3 hearts and 2 other cards. So the number of ways to pick 3 hearts is 13 choose 3. The number of ways to pick 2 other cards is 39 choose 2. Because of the 39 non-hearts, you're picking 2 of them. So that product, Works out to be 211, 926. It's over 2598, 960. And we end up with roughly 0.0815. Okay. Again, pick 5 cards without replacement from a deck of 52 cards. Find the probability that we pick at least 3 hearts. This is similar to the earlier problem, except we need to find the probability of picking 3 or 4 or 5 hearts. The expression on the left, that's the probability of picking 3 hearts. We've seen that before. 13 choose 3 times 39 choose 2 over 52 choose 5. Next comes the probability of picking 4 hearts. 13 choose 4, that's the number of ways you can pick 4 hearts. 39 choose 1, that's the number of ways you can pick 1 non-heart. Over 52 choose 5, the total number of ways you can pick 5 cards. Add to that the number of ways you can pick 5 hearts. That would be 13 choose 5, that's the number of ways you can pick 5 hearts from the 13 hearts in the deck. Over 52 choose 5, that's the total number of ways you can pick 5 cards from the deck. When you add those together, you get roughly 0.0927, as you can plainly see. Okay, so let's say we pick 5 cards without replacement from a deck of 52 cards. Find the mean number of hearts we pick. As in the previous problem, the probability is going to be R, the number of trials, in this case, the number of cards we pick, times N1 over N1 plus N2. That's, again, the probability of success on one particular trial. So that's 5 times 13 out of 52. In other words, 5/4. Now let's look at the 2015 Society of Actuaries Sample Exam P, problem number 132. A store has 80 modems in its inventory, 30 coming from source A and the remainder from source B. Of the modems from source A, 20% are defective. Of the modems from source B, 8% are defective. Calculate the probability that exactly 2 out of a sample of 5 modems selected without replacement from the store's inventory are defective. So here's the way we do this. We have 80 modems, 30 are from A, 50 are from B. From A, 20% are defective. 20% of 30 is 6. And from B, 8% are defective. Well, 8% of 50 is 4. So there are 10 defective modems, 6 plus 4, and 70 non-defective modems. That's the rest of the 80 modems. We want to find the probability that exactly 2 out of a sample of 5 modems selected without replacement from the store's inventory are defective. This is just like the picking balls from an urn problem or picking cards from a deck problem. So again, if we have N1 defective modems and N2 defective modems for a total of N1 plus N2 modems, well, we pick R modems. The probability that X of the R are defective if we pick without replacement. Again, just the formula we've seen before. That would be N1 choose X times N2 choose R minus X all over N1 plus N2 choose R. Now in this particular case, X is 2. We want to know the probability that 2 of the modems are defective. N1, the number of defective modems, would be 10. N2, the number of non-defective modems, is 70. X is 2, which means R minus X. In other words, 5 minus 2 is going to be 3. And N1 plus N2, total number of modems, is 80. R, the number of modems we pick, is 5. So we've got 10 choose 2 times 70 choose 3. All over 80 choose 5. That works out to be 0.1024, etc., or roughly 0.102. And so the answer is C.